Hi everyone, in today's challenge we are going to solve this problem. The problem name is unique binary search tree part 2 and the problem number is 95. Alright guys, so first of all what we are going to do? We are going to clearly understand the problem statement. After understanding the problem statement, then we will move to the logic part. In the logic part we are going to see how we can solve this problem. What is the logic we are going to use to solve this problem. So after understanding the logic part, then we will move to the implementation part. And in the implementation part we are going to implement our logic in Python, C++, Java and JavaScript programming language. Fine guys, and guys, if you want to have a look on the solution which I am going to write in this video for Python, C++, Java and JavaScript programming language, I will share the link in the description. You can go through that particular link and you can find all the solution, right? Fine, now let's see what this problem says. So let's understand the problem statement. Fine, so problem says given an integer n, return all the structurally unique BST means binary search tree, which is exactly n node of unique value from 1 to n. Return the answer in any order. Simple thing guys, we are given first of all n only. We are given one input that is integer, and that is nothing but have variable name n, right? Now we need to find all the unique binary search tree which we can which let me just first of all show you here. So we need to find first of all the unique binary search tree which contain nodes from 1 to n. That makes sense, right? Which contain nodes from 1 to n means if there is n is 3, that means we need to find all the unique binary search tree where we can have one node, two node and three node, right? There should be exactly n node with 1, 2 and 3 value, right? Means range of 1 to n. I hope it makes sense, right? After that we need to return all these unique binary search tree. Simple thing, right? But I know you may not get with this particular statement, so let's understand with the example. So in the first example we have nothing but n is 3, right? So n is nothing but 3. You can see in the first example. So they have written as five binary search tree, right? So we can make five unique binary search tree with exactly three nodes, and where nodes are coming like 1, 2 and 3. So you can see the example. The first way of making a unique binary search tree is nothing but 1 at the root node, third is the right node, and then 2 is the left of third, right? And the second way is nothing but 1 is the root node again, but 2 now this time on the right node, and 3 also right of 2, right? You can see this is right splitting, right? And the third one is nothing but 2 as the root node, where 1 is on the left of 2 and 3 is on the right of 2. So if you don't know, let me just tell you one more thing. If you don't know what is a binary search tree, so guys, binary search tree is different from binary tree. Binary search tree means a root node. If you have a root node, then left side always will be less than this node, and right side will always be greater than this root, right? So here if you will see in structure in this first three example diagram, we can see that 2, if we are taking 2 as a root node, so left side is always a less than of 2 and right side is always a greater than 2, right? Same in for example, you can see 3, if we consider 3 as a root node, so left side should be also always less than this 3, right? So you can see 2 which is less than 3, then 1 which is less than 2, right? And we are considering again a 3 node, and then you can say we have taken a left node 1, so that means nothing, we cannot write 2 here, right? Because now 2 will be greater than 1, so we have right in the right side of 2. You can see if you will focus at 2 which is greater than 1 but it is a less than 3, right? So that means it come on the left part of 3, but it should not come on the left part of 1, it should be come on the right part of 2, right? So we find five possibilities, right? We find five unique binary search tree where all the binary search tree have exactly 3 nodes, and the range is nothing but the value of unique nodes is 1 to 3, right? 1, 2 and 3, right? It makes sense, right? So we have to return all these nodes. We don't have to return the count, we have to return all these nodes. So how we can do this, we will see in the logic part, but for now I hope you understood the problem statement. So let's see the second example. And in the second example we have nothing but, we can see, let me just scroll it little below. So you can see in second example we have only one. That means I think there is only one node, right? We need to find all the unique binary search tree which contain only the one node. So you can see guys, we can only make one binary tree where one is only always going to be root node, right? So this is nothing but a BST. So this is the only possible BST we can create with the one node. So we have written that only, right? You can see we have written only one node. I hope guys you understood the problem statement. Simple problem statement. Let me summarize this. The first thing in nothing but we are given one integer, that in nothing but we can say n. Second thing is we have to find all the unique binary search tree with exactly n nodes, and all the node value varies from 1 to n, right? And all the node values should come, right? Means 1 to n should be present in that particular binary search. Fine, it makes sense, right? Now guys, let's see how we can get all the binary search tree, right? All the unique binary search tree of exactly n node. So let me write a logic part. And guys, logic is going to be really easy. If you have seen my last, I don't remember, the problem name was all possible binary, right? So if you have seen that problem, just similar to that, nothing changed, just a small one line of condition will change, nothing but exactly going to be same, right? Let me show you how it's gonna work from scratch, right? Maybe you have not seen that particular problem. So what I'm gonna do, I'm gonna say okay. So I'm gonna give an example of this first example only, n is equal to 3. So we are gonna see how we can get all these five node, right? All these five unique binary search tree where n is 3. So if you understood this, that means you can create visualization for n is equal to 5, 6, 7, 8 as well, right? And see guys, one more thing, a constraint here is nothing but n will not more than we can say 8, right? N will always be less than or equal to 8, and will never be more than 8, right? Fine, this makes sense. Like we can use a approach like n square, right? And cube as well. Fine, that makes sense. So what we can do now guys, n is equal to 3, right? So n is equal to 3, that means nothing but we need to find all the unique binary system with exactly, which have exactly n node, means 3 node, right? So what we can do, we can simply say guys, n is equal to 3, right? So what I can say here, I'm going to say here because I need a more space. So here I can say, first time I'm going to put for 1, second time I'm going to put 2 as a root node, third time I'm going to put as a 3 as a root node. So because I have n is equal to 3, right? So my range is nothing but 1 comma 3. So now again I'm going to remove this, I'm going to say my range is nothing but initially 1 comma 3. See the recursion part here, right? What is going to vary over here? Here the thing which is going to vary is nothing but start and end. So currently my range is 1 2 3, right? I hope it makes sense, right? I need all the binary search tree which should have exactly 1 2 and 3 node, right? That makes sense, right? Means this makes sense, right? I hope. So now what I can do, I can say, let's keep 1 as a root node, let's keep 2 as a root node first time, let's keep 3 as a root node. I can make any 1 as a root node, right? Because I have the range 1 2 3, right? Fine. Now if I am taking 1 as a root node, so I have to only evaluate what is binary search tree. Binary search tree, such tree where left side always be less than the root node, right side will always be greater than the root node. So if I'm taking a 1 as a root node, so left side will always be less than 1. And you know that we have a range 1 to 3, right? Initially we have a range 1 2 and 3. So I can say there is nothing left, there is no number present which is less than 1, right? So I'm going to say it is going to be null. But right side we have something, right side we have now two number 2 and 3. So I'm going to say right side we have 2 3 range. Same goes for 2. So if I'm taking a 2 as a root node, so what are the number which is left less than 2? That is 1 only. So the left range is going to be 1, right? And right range is going to be 2 comma 3. No, 2 comma 3, only 3, right? Why? Let me show you here. So the number which is less than 2 is 1 only, and the number which is greater than 2 is nothing but 3 only, right? So this is clearly sorted. This no need to traverse again. So we can say this is one possible binary search tree, right? 2, 1 and 3. And you can see in the example as well. If I just scroll it above, you can see we have one diagram with that particular also, 2 1 and 3, right? So we got for now we got one our BST which are having exactly 3 node with 1 2 and 3, right? I hope it makes sense. Now what we are going to do, we are going to say fine, we got this, let me just make it clearly. And now if we are taking a 3 as a root node, so you know that left side is going to be always less than 3. So you can see we have two range, right? 1 2 1 and 2, which is nothing but less than 3. But right side there is going to be nothing but and null. I hope it makes sense, right? So for now you have understood the first, we can say the level. The first level what we have done, we have put all the node as 1 2 and 3 as a root node, and then we have seen what is the left, what are the number which can go in the left side, what are the number which can go on the right side, right? So left side there is nothing range, on right side we have 2 comma 3, and left right side there is only one number, so we have not passed any range, we have just passed one and here 3, and so on for 3 as well, right? Now let's see the second browser which will help you to understand recursion, how recursion gonna work. So I'm gonna different adjust color. So second is nothing done, is not gonna traverse again, so we can say fine. But 2 comma 3 can be traverse, right? So what I am gonna do here, 2 comma 3 is again a range, right? So this was also a range, initially recursion function 1 comma 3, 1 2 3, right? So this is also range. So we can say this is the same function which we have just traverse. So again I'm gonna put 2 as a root node, 3 as a root node, right? I hope it makes sense, right? If I'm putting a 2 as a root node, so what I can say now range my 2 and 3. So if I'm putting a 2 as a root node, so the number which is less than 2 should become on the left side. But you can see there is no number less than 2, right? Is there any number less than 2? No, there is no number less than 2, right? But there is a number greater than 2. So we are going to put 3 on the right side. Same goes for 3. Is we are going to put a number less than, which are less than 2, right? So there you can see we have a number only 2. We have a number which is less than 2. But there is no number on the greater than 2. So we are going to put null on the right side. Same, right? So now guys, if you focus on this part, just try to focus on this part. You can see we got two binary STB here. How? So if I just make it 3 here, so guys initially 1 was there, then we got null on this side, but here we have a 2 root node. First time 2, and same I draw here null, second time 3, right? I hope it makes sense. After that from 2 we got 3 only. Here is null, here is 3, and here we got null, right? And here we got 2, here we got null. So we got 2 binary STB, right? So from one root node. And in the example, if we'll focus here, we have 2 binary tree with the root node 1. So that means we have covered 3 diagram, making a sense, right? So we have covered 3 diagram. Now let's move to the head. So we have sorted for the first and second node. Now let's move all these things. Sorry guys. So here what I'm going to do, I'm going to say again, we have sorted for 1, 2 we don't need to traverse because you can see we have only one node, fine. But for 3 we need to traverse because we have one range here. So same guys, if we have range, we can say one can be a root node or 2 can be root node, right? If 1 is a root node, so we can put 2 on the right side, and left side there is going to be none. If 2 is a root node, so we know that there is a number present less than 1, and less than 2 is 1, so we're going to put 1 on the left side and right side is none. So if you'll focus here, this is also 1. We can say we got 2 binary search tree here with the 3 node, right? 3 as a root node. You can see if I put 3 here, then I have a right side null, directly null here. But left side, we have either 1 or let me make another tree with the 2, right? Because there could be on the left side, there could be 2 node, right? 1 or 2, right? If there's a 1, then we can say right side 2. If there's 2, then left side 1. So this is nothing but we can say 2 possible binary search tree with a 3 node, 3 as a root node, right? So that means nothing but we got these 2 possible binary search tree, and we can see this is also present on the this side, right? You can see this side. So that means we have covered all the 5 diagram, right? So I hope guys now you understood the logic part. What actually we have to do, we have to just make a one recursion function where we are maintaining a start and end. So you can see if we are making start and end, we have to traverse still from start to end, and we have to keep all the node as a root node. So here 1 to 3 were start range, start and end there. So we have put 1, 2, and 3 as a root node. Then we have to check how many how many numbers we have less than 1, and how many number we have greater than 1. We have to put on the left side and right side. If we are getting again a range, then we have to keep traversing all this function, right? Simple thing, nothing makes sense. So recursion base condition is going to be nothing but when your start is greater than n. So you can see guys, start is when your start is greater than n, then you have to return this null. And if you can see guys here 1 and this, right? So let me just highlight here 1. So here why I have written null, because I know if I'm going to pass something here that will met with this condition, start will always be greater than n, right? I hope it makes sense. So now let's move to the implementation part and let's see how we can implement this condition, right? Implement this logic. So first of all, I'm with the Python, right? So what I'm going to do, I'm going to define one function sol where I'm going to maintain start and end, right? So what I can say if start is greater than, so I have to return what I have to return simply a function which is nothing but let's say none, right? I have written this one, fine. But if start is not greater than n, that means we have some range, right? If we have some range, so what we can do, we can traverse over all the range for a range of start comma n plus 1. Why n plus 1? Because I want to take 3 number as well. If I have range 1 to 3, then I want to take 1, 2, and 3 as well, right? So I take n plus 1, fine. Now after that, what I'm going to do, I'm going to say for left side you have to calculate. Left side they are going to calculate which calls sol function, and there I'm going to pass for this range. Range is going to be start to I minus 1. See guys, let me show you with the diagram. So what I'm going to do here, I'm going to say okay, we have taken a 1 as a root node. So if I'm taken a 1 as a root node, so what will be my start range here? Start range will be 1, 2, the number this minus 1, so this is nothing but 0, 1 comma 0, right? This is my start range, and 1 to 0, 1 to 0, and you can see start is greater than, start was 1 and n is 0, so start is greater than n, so we have to return null, right? So we are returning a null. And similarly, what is the range for right side? Right side will be greater than 1. 1 plus 1 is 2, 2 to the end part 3. So same thing I'm going to say. I'm going to say right side. We are going to solve, and here going to be I plus 1 to end. Why I have taken I? I is a root node, right? So I have removed I from this range as well. I have removed I from this range as well because I is a root node. So once this is calculated, we are going to say 4. All right. So for left node in left side, for right node in right side. So I'm going to say create a root node. Root is going to be 3 node, and here I'm going to pass over I. So now I have created a root node with I. So you can see here with the 1, because I have skipped here as well on the left and right range. Now I have created I. I can say root of left is going to be nothing but left side, left node, and root of right is going to be nothing but, let me add right, is going to be nothing but right node. Let me add right node, right. Fine. So this is done. After that, what I have to do, I have to insert this root 1 in my result. So I can say result dot you can say append this particular root node, right? I have to define result as well, so I can say result is going to be nothing but, fine. This makes sense, right? After that, we can say okay. Now at the end, you can call this function for 0 comma not 0 from 1 comma n, right? And after that, whatever this is going to return, you have to return that part. Simple thing. It makes sense, right? Let's try to submit this code. Simple thing, guys. I hope it makes sense. You can see that we got an error. Right side is not defined. Why it is not defined? Left side, right side. I forgot to put h here. Alright, so it's my bad. Let's see. And it taking a time. Definitely you're gonna give a right answer, right? I want to see why it's taking this much time. So do we are getting a none type is not iterable. So what I have done here, I have none type is not iterable. So see guys, we have start and end. If start is greater than end, we have to return nothing but. Alright, so the issue is nothing but guys, I haven't written this result. It's my bad. I don't know what I am doing here. Now let's see. So return result. Now it's gonna pass it. You can see guys, both the test case pass. So let's try to sum this code. So we have to return it right so that next recursion call can take this particular number, right? Fine. You can see guys, it successfully got submitted. Now let's move to the next programming language and C++. And here, first of all, we are going to define one function sol. So let me define here one function sol, and the data type is going to be nothing but same vector tree node. The name is sol, and here I'm going to pass start and end, right? Fine. And after that, I can say start is greater than end. So what you can say? You can say return. What you are going to return? First of all, I have to define this other thing. As I'm going to return a vector of tree node, so let me define here only vector of tree node. The name is result. So I'm going to say before returning result dot add, we can say add node add. We can say pushback, right? Pushback null. So we can say null ptr. After that, we can say result return result, right? Return result. But if start is not less than let me decrease the size. Okay, one more size, fine. Now guys, I can increase the size, right? So I'm saying that guys, if start is not greater than end, right? That means nothing but what we can say. If start is not greater than result, then we can say simply move to all the possible root node, right? So we have to take all the nodes which in that given range. So we can say for int I is equal to we can say start and I less than equal to end, and let me write end and I plus plus. So I'm gonna say take all the node as a root node. So I'm gonna say fine. If I'm taking I as a root node, so I'm gonna call a sort function where start, where our start is gonna be start only, but I is gonna be I minus one, end is gonna be I minus one because I have taken a I node. So I know that I minus till I minus one node is gonna be I less than I node, right? And I'm gonna call same function for I plus one to n. So this is gonna be for the right side. Fine. So now I'm gonna say assign this whole thing into a auto left side. I know the data type, but you must know the data type before writing auto. Here the data type is going to be vector tree node star, right? But for now, I'm going to write auto only. Auto right side. I hope it makes sense. So let me do a little fast here because you know all these things, right? This is basic. So what I can say for right. So we got left and right side. So I'm going to say for left node, right? So I can say for auto left node in our we can say what in our left side. So we are going to toss all the left node, and for auto right node in our right side. So we are going to traverse over the right side, and after that we are going to say create a new node. So we can say tree node root is going to be nothing but new tree node, and here we're going to pass our I. So this is our root node I, and after that all this root node we are going to send our left and right side, right? Root of left is going to be nothing but we can say this root of left is going to be left node. Let me write a left node, and root of right is going to be nothing but right node, right? So what I have done here, I have defined a root node, and after that I have assigned their left and right child. Once this is done, after that we are going to say, alright. So after that we have to put in our result dot push, not push back, right? Push back. We are going to append this loop, right? So now once this is done, then we are going to say return and then return result. Now let's call this function here with this range of 1 to n, and return whatever the output they are going to give. So return that. Now let's see whether it's fine or no. Simple thing guys, we take all the left side and all the right side. We have covered all the right possibilities, then we have done this part. And let me show you the example here as well. So you can see that we taken one as a root node, but here we got, you can see we got two possibilities, 2 and 3 as a root, this right node, right? So one time we have pushed 2, one time we have pushed 3, right? So the same thing we are using here. Now let's try to submit this code. So you must know the logic part. If you are directly seeing the implementation part, it will not going to help. You must have to see the logic part as well, right? Fine. Now let's see the next programming language. Nothing but we can say Java. And in the Java, I'm going to say call a function sol with a range of 1 to n, and here to add then return whatever the sol function return. So let's define our sol function. So I'm going to say okay list and tree node, and here we can say what we are going to say. We are going to say our sol function, right? Sol int star. Let me get in node it. Fine. Here we can say if our star is greater than n. So we can say what we have to do. We have to do nothing but we have to add, first of all add null. and then we have to return this result. But result is what? Result is nothing but list of tree node, right? So list of tree node, and here we can see result, which is going to be nothing but new. What is this? New array list, right? I hope it makes sense. Fine. So, but if start is not greater than end, that means we have some range. So we are gonna go to all the possible range. For int is equal to start, I less than equal to end, I plus plus. We are gonna assign each as a root node, right? So we are gonna say fine. I'm gonna take a u as a root node. So what I'm gonna say left side is gonna be let me write a list of tree node. We can say left side is gonna be nothing but always gonna be source function. That's range is gonna be start to I minus one, and right side, as we know now, right side is gonna be nothing but what sol I plus one to start, right? After that, once we got all the left and right possibilities, we are going to traverse all these possibilities. We can say for tree node, node, left side, for tree node, node, right side. Let me put small s. Once we got all the possibilities, we are going to assign each left and right as a root node of this I. So we are going to create a root node tree or node, and here we're going to say root is going to make a new tree node, and here we're going to pass our I. That means we have created a I as a root node, right? Now once we have done this, we are going to say root of left is not root. Root of left is going to be this left node, and root of right is going to be right. Fine. Once this is done, then we are going to say put this root as our result. So result dot add this root. Once this is done, and then we are going to return this our result. Fine. Now let's see whether this we can find or not. You can see we got an error. The error is nothing but it has not taken null all this part, right? So why it has not taken, let's see that part as well. So let's debug this one. So we have given a range I plus one start, right? So that's why it's not taking the right side. We have to pass end. So now let's see whether it's working fine or not. You can see guys, both test case passed. So let's try to submit this code as well. And I hope guys it will also gonna submit. So you can see guys, it successfully got submitted. Now let's move to the next programming language, which is we can say JavaScript, the last programming language. And here in the JavaScript, what we are going to do, we are going to say first of all, define one function const sol. As this is JavaScript, we can define nested easily. Fine. And here we are going to take a start and end. Once we have done this part, we are going to say what? We are going to say nothing but fine. We are going to say if start is greater than end. So what you are going to do? You are going to say return. First of all, you have to result dot push. You have to return push null. Then you have to return result, right? And we haven't defined result, so let's define result here as well. Result. Fine. So let me put semicolon as well, right? Fine. Once this is done, then what we are going to do? We are going to say fine. Now, if start is not greater than end, that means we have some range, valid range. So we are going to go to all the range. For let is equal to I is equal to start, I less than equal to end, and I plus. And I'm going to say fine. If I go to this range, then I'm going to calculate left side and right side. So I can say left side is going to sol start for my minus one, and right side uh, is going to sol and I plus one to start not to start, we can say end. So once we go to left and right side, so we pass a valid range both. Now after getting a left and right side, then what we are going to do, we are going to say move to all the nodes which you have left and right side, make all the combination. So we are going to say for each left side, for const left node of left side, for const right node of right side. Here we are going to say okay, we have put string here. Here we are going to say fine. Now we are going to create a new, we can say tree node. So we can say let root is equal to new tree node, and here we can pass our I, which is a root node. Then we can say fine, our root node we have already got. Now with root of left is going to be nothing but left node, and root of right is nothing but going to be right node. Once this is done, we are going to say result dot push this root, and the out of this for loop we are going to say return our result, which is containing all the possibilities, right? Once this is done, we are going to call this function. We can say let's call this function sol 0 or not 0 1 to n with the range, and after that return whatever this function return, right? And let's see whether this is fine or not. So I hope guys it should work, right? But we got an error, right side is not present, right node is that we had a right side, right? Okay, fine. Let's see now. Hopefully it should work right. Let's see. So you can see guys, both the task is passed. So let's try to submit this code and let's see whether it's getting passed or not. And you can see guys, it's successfully got submitted, right? So we have done the implementation with Python, C++, Java, and JavaScript programming language. I hope you understood the implementation part. If you have any kind of doubt in the problem understanding part, logic part, implementation part, you can directly write in the comment section. I'm always there to help you, right? So if you learn something new in this video, don't forget to hit the like button and subscribe my channel. Meet you in the next video.